let's talk about some basic applications of integration. The first and most basic application is the average value of a function. So imagine I had a function r of t that gives me the rate of products sold at any particular time. So if its graph looks like this, and we wanted to find the average rate at which products are sold, what we'd have to do is first find the total number of products and divide that by the total time. So the way we find the total number of products with the rate function, well, it would be the area under the curve. So it would be the integral. And then the total time is simply the difference in t. So if I wanted to find the average value from, say, 3 to 7, it would firstly be the integral of r of t from 3 to 7 divided by the range. And here the range is 7 minus 3. So it would be the integral from 3 to 7 r of t dt over 4. And this is the average value of a function. And this works for any function. Alright, for example, let's find the average value of the function y is equal to 3x squared on the interval 3, 5. So firstly, we have to take the integral, which is the integral from 3 to 5 of 3x squared dx, and then we have to divide by the range. Now the range here is just 5 minus 3, which is 2. Now this is just equal to integral from 3 to 5 from 3 to 5 is equal to 1/2 of 125 minus 27, which equals 49. So the average value of this function on this interval is 49. And again, all we have to do is take the integral and divide by the range. Now let's talk about the mean value theorem for integrals. So you may remember the mean value theorem for derivatives, which is this. If I have a continuous and differentiable function along some interval a to b, so this is a, this is b, and I took the average rate of change in between a and b, there must exist some point along this interval where the derivative is equal to this average rate of change. What that means is, imagine this blue line has a slope of m, then there has to exist some point c on this interval where f prime of c is equal to m. And as you can see visually here, that does happen. Now the theorem guarantees that there's at least one. In this visual example, there's likely two. So this is the mean value theorem as it's used for derivatives and rates of change. But there also exists a mean value theorem for integrals. So what this is saying is that there has to exist some value of c where f prime c is equal to the average rate of change. And the average rate of change is f of a minus f of b divided by b minus a, which is the range. Now this also applies to integrals, and all we have to do is rearrange this by moving this over here. But first, let's get a visual understanding of the mean value theorem for integrals. So imagine we had this curve f and we wanted to find the area. Well, the first thing we know is that, it's the area under the curve. It has to be larger than this green rectangle over here, because the green rectangle is taking the minimum point of the function f and multiplying that by the entire range from a to b. So we know that the area has to be larger than the green. Secondly, we know that the area has to be smaller than this red rectangle over here. We know this because the red rectangle was obtained by taking the maximum value of the function and multiplying that by the range. Because this function is continuous along this interval, we know that in between the green rectangle and the red rectangle, there has to be some rectangle where the area is equal to the integral. And let's write out what this means. So we know that green has to be less than, the actual integral of f of x from a to b, which has to be less than the red. And therefore, there has to be some value in between the green and red that's equal to this integral. So just to be more explicit, we'll say that f of x minimum on this interval times the range, which is b minus a, is less than the integral, which is less than f of x max times b minus a. This means there has to exist some value c where f of c times b minus a is equal to the integral. Now, the reason this relates to the mean value theorem is because it looks the same if I were to move this down here. So f of c is equal to, now the integral of f of x, we're going to call it capital F, so is equal to f of b minus f of a over b minus a. This is just the average rate of change from b to a, and f of c is the derivative of capital F. So the formula is essentially the exact same as the mean value theorem for derivatives, but the intuition behind it is slightly different because that comes from areas and integrals over here. Now, when you're doing integrals, you'll also see a lot of problems about particle motion. And this, again, it isn't just integrals, it's also differentiation. So this relates to x, v, and a graphs, which you probably know if you've done physics. So x is a particle's position, v is its velocity, and a is its acceleration. And the link between these two is that to go from position to velocity, you simply take the derivative, and to go from velocity to acceleration, you take the derivative again. Similarly, if I had acceleration and I wanted to find velocity, you take the integral from here to here, also another integral. Alright, so let's imagine I have a problem that says my acceleration is a function of time and it is mapped by the function 2t squared. Let's say my initial velocity, so v0, is 5 meters per second, and they're asking for my displacement, so my change in position, my delta x, in 10 seconds. So first, I want to know my position, so I want to know my position function. So let's start with acceleration. So you know that a is equal to 2t squared, and to get to position, first I have to get to velocity. So I'm going to integrate. So the integration of acceleration with respect to time is velocity. So my velocity is equal to t cubed times 2 over 3 plus c. Now this c, because we know our initial velocity is 5 meters per second, our c is just equal to 5. So now we have the function v is equal to 2t cubed over 3 plus 5, and then to get to position, once again, I'm going to integrate. So if you integrate velocity with respect to time, you integrate this with respect to time, you get position. So now our position will be mapped by the function 2t to the 4th over 12 plus 5t plus our initial position. We don't need to know our initial position because we're not asked for it. We're asked for the displacement, which is equal to x minus x0. So we can say x minus x0 is equal to t to the 4th over 6 plus 5t. Since we're given that it's in 10 seconds, all we have to do is plug in. So it'll be 10 to the 4th over 6 plus 50. And this is your displacement, or your delta x, in 10 seconds. Now, this also works, anyway. If we were given the position and we were given the velocity, you could find the acceleration simply by taking the derivative. Now, when you're doing particle motion, there is an important equation that you might have to memorize, and that is this. When an object is falling, it experiences acceleration due to gravity, and that is given by this minus g constant. This is your initial velocity and this is your initial position, and this function just maps the position of an object over time. Now, the way you get this formula is very easy. So firstly, when an object's falling, the acceleration is constant. It is just due to gravity. So let's just start with acceleration. To get to velocity, we integrate, and so we get our velocity is equal to at plus now some constant c, but this c is just our initial velocity. To get to position, we integrate once again, and then we get at squared over 2 plus v0t plus x0. And this is our position. Now, the reason you have to know this form with minus g is specifically in projectile motion. When you throw or drop an object, the acceleration will be this g constant due to gravity. If you're doing in meters per second, g is equal to 9.8 meters per second. And if you're doing in feet, it's typically 32 feet per second. So if I was solving a problem in feet per second, I would say minus 16t squared plus v0t plus my initial position is equal to my position. And lastly, the most important part of this video is areas between curves. So we know an integral is the area under a curve. So the integral of f would simply be all of this area right here, and the integral of g would be this blue area right here. Now, if I wanted to find the green area in between, it's simple. It's simply equal to the area under f, so the integral of f minus the integral of g dx. So all we have to do to find the area between two curves is take the integral of the difference of the functions. For example, let's find the area between the functions 5x plus 3 and sine x from 0 to pi. So let's see what area we're trying to find. Firstly, we have a function 5x plus 3, which looks like this, and then we have sine x from 0 to pi, which looks like this. So what we're trying to find is this red area over here. Because it's from 0 to pi, we know those are our bounds for integration. So it's going to be the integral from 0 to pi of 5x plus 3 minus sine x, all with respect to x. When we integrate this, we get 5x squared over 2 plus 3x plus cosine x. And we simply need to evaluate this function from 0 to pi. When we plug in pi, we get 5 pi squared over 2 plus 3 pi, and then cosine pi is -1, so -1. When we plug in 0, we get 0 plus 0 plus 1, and we'll have to subtract it. So our final answer is the difference between these two, which is 5 pi squared over 2 plus 3 pi minus 1 minus 1, so -2. So this is this red area over here between the line 5x plus 3 and the curve sine of x. Now, importantly, sometimes they won't give you explicit bounds, and they'll instead ask you to find the region that itself is bounded by the two curves. So for example, y is equal to x squared and y is equal to the square root of x. Find the region bounded by these two curves. Well, if we were to draw a graph, y is equal to x squared looks like this, and y is equal to square root x looks like that. So there are two intersection points, one at 0 and one at 1, and they want us to find this area in between. So firstly, we have to find the intersection points, and we do that by saying x squared is equal to square root x. And we know this happens at two places, x is equal to 0 and x is equal to 1. These are our bounds of integration. Our integral becomes the integral from 0 to 1 of x squared minus square root x with respect to x. This becomes x cubed over 3 minus x to the 3 over 2 divided by 3 over 2, evaluated from 0 to 1. When we plug in 0, we get 0 for everything, and when we plug in 1, we get 1/3 minus 2/3, which is -1/3. Remember, this is a negative number, but we're asked to find area, and area is an absolute value. So we're just going to take the absolute value of -1/3, which is 1/3. This also means that when you have something like this, typically they want you to take the top function and subtract it from the bottom function. So it would be square root of x minus x squared, and that would be your integral. Because we did it the other way, we got a negative, but just remember, if you end up with a negative number, you can always just take the absolute value of the whole expression, because the area is still the same. So find the area of the region bounded by the curves x is equal to y squared and x minus y is equal to 2. So firstly, let's see what our graph looks like. X is equal to y squared is a sideways parabola, so it looks like this, and x minus y equals 2, that means y is equal to x minus 2, so that is a line that looks like this. So the region that's bounded by these two curves is this region over here. Because these functions are like this, and it crosses the x-axis, we are going to actually integrate with respect to y. So we can integrate this way. This means we need to find the y values at which these functions intersect. So I'm actually going to write x in terms of y. So x is equal to 2 plus y. And now we're going to find the intersection points. So y squared is equal to 2 plus y. And if you were to solve this, y squared minus y minus 2 equals 0. Y is equal to 2 and -1. So these are our bounds of integration. We're going to integrate from y is equal to -1 to y is equal to 2. So remember, we need to integrate over this length over here, which is one x coordinate minus the other x coordinate. And we're integrating this way, so it's with respect to y. So finally, we get the integral from -1 to 2 of y squared minus 2 plus y. So -2 minus y with respect to y. This becomes y cubed minus 2y minus y squared over 2 from -1 to 2. So when we plug in 2, we get 8 over 3 minus 4 minus 2, which is equal to minus 10 over 3. When you plug in -1, you get minus 1/3 plus 2 minus 1/2, which is equal to 7 over 6. Finally, we need to find the difference of these two. So our final answer will be minus 10 over 3 minus 7 over 6. This is equal to minus 27 over 6, which is 9 over 2. Again, it's negative, but because we're asked to find area, it's the absolute value. So the absolute value of -9 over 2 is 9 over 2. Let's go over one more example, and this one's slightly harder. The region will be bounded by three curves. Y is equal to 12 minus x squared, y is equal to -x, and y is equal to 4x. So to solve this problem, let's first see what our region looks like. So we have y is equal to 12 minus x squared, which is a parabola that looks like this. We have y is equal to 4x, which is a steep line that goes this way. And we have y is equal to negative x, which goes this way. So the region that's bounded by all three of these curves is this region right here. We can't do this in a single integral because they're two separate lines that bound the region. So we're going to break it up. Firstly, we're going to break it up into this region over here, which is bounded by y is equal to negative x and the parabola. And then we're going to find a second region over here, which is bounded by y is equal to 4x and the parabola. So let's start by finding all of our intersection points. The first intersection point requires that 12 minus x squared is equal to negative x, which means x squared minus x minus 12 equals 0, x minus 4x plus 3. Now, we're not really concerned with x is equal to positive 4 because that point's all the way down here. So we're just going to deal with x is equal to negative 3. Now, for the second one, we have to say it's equal to 4x. So 12 minus x squared equals 4x. X squared plus 4x minus 12. X plus 6. X minus 2. We're not concerned with negative 6 because that point's all the way down here. So we're going to deal with x is equal to positive 2. Now, the other endpoint for both of these integrals is 0 because that is where these two lines intersect. So we're going to integrate from negative 3 to 0 and 2 to 0. Now, this will be the integral from negative 3 to 0 of 12 minus x squared minus negative x, so plus x. This is equal to 12x minus x cubed over 3 plus x squared over 2. From negative 3 to 0. When we plug in 0, we get 0 for everything. And when we plug in negative 3, we get minus 36 plus 9 over 2. Now we can just simplify by putting everything over 2. So 72 plus 18 plus 9 over 2 minus 72 minus 27 is equal to 45 over 2. So this is the area of our first region. Remember, it's negative, but because it's area, I'm taking the absolute value. So it's 45 over 2. Now let's look at our second integral. So our second integral is the integral from 0 to 2 of 12 minus x squared minus 4x. This becomes 12x minus x cubed over 3 minus 2x squared. From 0 to 2. Plugging in 0, everything cancels out. Plugging in 2, we get 24 minus 8 over 3 minus 8. So this gives us 72 minus 8 minus 24 over 3, and that gets us 40 over 3. Now all we have to do is take the sum of these two regions. So our final answer is 45 over 2 plus 40 over 3, which is 135 plus 80 over 6, which is equal to 215 over 6. This is our final answer of the area bounded by all three of these curves.